Hello everyone, today we'll be going over problem 4 on the 2025 AIME 2. So, first of all, by looking at this question, it wants us to find the product of this big whole thing. And when you see a long sequence of product where everything looks really similar, a bunch of logs, on top and bottom, you'll think of telescoping, right? There's no way they'll expect you to calculate every single thing. There has to be some sort of pattern and everything starts canceling out. So, the first thing I noticed when I saw this question, well, apart from it being extremely scary, was that, look, the bases, there's pairs of bases that are the same. Look, there's fives, there's two sixes, and that made me think about one logarithmic identity, which is really important in questions like these, by the way. If you don't know your logarithmic identities, you're good luck, you're going to struggle. But the one I thought about was this one. Log AB over log AC equals log CB. So, and then I also thought about this one, because once we use this on the pairs, so if we pair up each of the logs like so, we got the fives like here, the sixes here, sevens, and so on. And if you're wondering where the 64 and the 4 go, that's going to be on the first one. Come back to this later. But after we do this, notice how we also have this identity, which we can clearly use after applying this, because if we applied this on each of these terms, we'll end up with log 5 to a power of something of 5 to a power of something. And we can simply now just divide, and hopefully you can find a pattern, right? Again, we'll get back to this later. So, boom. So applying this identity onto each of these terms, we'll get their respective results from this identity over here. And if we use this identity, boom. So now what we have is this. So log 4, 5, 15 times log over all this first part. Again, we'll come back to it later. All of this is just the application of these two identities. So notice how instead of writing it in terms of 12, 21, 32, I wrote it into the term that's described in the pi notation, as in k squared minus 1 and k squared minus 4. And this will come in handy useful because notice how 1 and 4 are both square numbers, meaning that if we write it like this, there's a higher chance we can see like a pattern with difference of squares, as we can factor it, and there might be something that we can notice. But now let's come back to the first part. The first part actually has a really nice way you can calculate it. So the way you would do this is you would use the fact that if you have log A to the B of C, this is equal to log AC over B. And essentially, what you can do now is you can write as, so recall that 64 is 4 to the third power, right? You can write this as log 4, 5, 15 over log 4, 5, 3, 9, 6, 5, and this over 3. So this is the longer fraction. And we can simplify this by getting rid of that. We're putting it up here, right? And once again, using this, we can simply write this as 3 times 15 over 3965, which ends up being the value that we see here, 9 over 793. So essentially what we did is like so. So I just realized I did skip a step over here. I should have written this in the form of log 5, 53965 of log 5 to the 15th. But essentially, if you applied this identity and then this, you'll end up with 3 times this, which is 3 times 15 over 3965, which is 9 over 793. And notice how I've now factored out each of these difference of squares, right? We have 5 plus 1, 5 minus 1, over 4 plus 2, 4 minus 2, 6 plus 1, 6 minus 1, so on. And notice how for every single one of these fractions, we can do some canceling. So notice how we can cancel out the 5 plus 1 and 4 plus 2 since they both equal 6. 6 plus 1, 5 plus 2 both equal 7, all the way till the end. And that's not a coincidence, because notice how in the beginning, each one, right, each one is going to have k squared minus 1. And so notice here, each term is going to have k squared, so every k from, I believe it's from 5, from 5 to 63. The numerator is going to be k squared minus 1, and the denominator is going to be k minus 1 squared minus 4. And if you find out, so the numerator is going to be k squared minus 1, and the denominator is going to be k minus 1 squared minus 4. And this one, and there is going to be a factor of k plus 1 here. It's also going to be a k plus minus 1 plus 2, which is also k plus 1. So each of these have one of these terms times something. So now we've shown that each one of these fractions has something that we can cancel out. What else can we cancel out? Well, notice that although it's not pictured here, or you can write, there is going to be 5 minus 1 is 4, and in the next term there's going to be a 6 minus 2, and we can cancel those out. For the same reason, we can cancel all of these all the way up to 62 minus 1, because in order for us to have 61 as a result of something minus 2 on the denominator, that something will have to be 63, which is outside of our range. But for the same reason, we can cancel all of these, because 62 minus 2 is 60, and we need something plus 1 is 60, which turns out to be 59, which is indeed part of our range. Sorry, something minus 1 is 60, which is 61, which is which there will be somewhere here. So what we end up with essentially is this, right? Everything else cancels out. This is all we end up with. And if we solve, we get 93 over 13, which adds up, and which is in the form m over n, everything's in lowest terms, which adds up to 106, which is our answer. Thanks for watching.